In this video I'm going to look at electronic structure, building on a previous video on atomic structure where we saw an atom had a nucleus, which is a central core, which had protons and neutrons in there, and this was orbited by electrons. We saw that the electrons orbited in shells or energy. So for example, lithium would have looked like this with 2 electrons on the inner shell and 1 on its outer shell. Then we would have seen another element like sodium would have had 2 electrons on an inner shell followed by 8 electrons on its second shell and 1 electron on its outer shell. And then if I went further on to potassium, we would have seen that that would have had an extra shell of electrons. So we have seen this idea where we can count the number of electrons on each shell, and potassium would be 2, 8, 8, 1. And that's called an electron configuration. In this video we're going to look at how we know of this certain idea that there's energy levels or electron shells, which we will call energy levels in a minute, and build on that theory. So we're going to look at how there's evidence for electron shells, and to do this I'm going to incorporate a new idea that these electron shells aren't just shells of electrons. We know the electrons orbit the nucleus, but they do so in certain energy levels, which each are a certain distance from the nucleus. So if I redraw the sodium atom here with 2 electrons on its inner shell, I'm actually going to show you that this inner shell is actually represented by an energy level, and we're going to call that the first energy level. Okay, where n is what is called a principal quantum number. Now, the second energy level, n equals to 2, okay, is quite a bit of a distance away from the first energy level. It's just a further distance from the nucleus. And then energy n is equal to 3, the third energy level, is further away still. So we now need to look at where we get evidence for this theory of energy levels. And to start with, we're going to look at the electromagnetic spectrum. So the electromagnetic spectrum looks something like this. Electromagnetic waves which exist travel through space and matter depending on the wavelength, okay? And the velocity of their travel, i.e. the speed, relates to the wavelength and the frequency. So wavelength equals the distance between successive waves. So the crest of a wave here and here. Now that distance is known as a wavelength. Okay, so we can see that as we go further to the left of the electromagnetic spectrum, we get a shorter and shorter wavelength. Another unit of measurement is the frequency. The frequency equals the number of waves that pass through a given point per second. So here we'd have quite a low frequency because it would take longer for this to travel through, whereas here our frequency would be quite high. So up at this end of the electromagnetic spectrum, the waves have a short wavelength but a high frequency and therefore higher energy. All energy can be classified, okay, according to this spectrum here. Now we know that you're probably used to radio waves, microwaves, infrared radiation, visible radiation, and ultraviolet light, X-ray and gamma ray radiation. It's the visible part of the spectrum that allows us to see certain objects because they absorb light in this part of the spectrum. So this is known as the electromagnetic spectrum. Now I'm going to discuss how we get our evidence for energy levels. And to start with, I'm going to talk about what happens when white light passes through a prism. As you can see from this image, when white light passes through a prism, we get a continuous spectrum of colors. Now, when energy is supplied to individual elements, they emit a spectrum containing emissions of a particular wavelength, i.e. you get a certain color. So if we take a sample of a substance and then we supply it with energy, what we see certain colours appearing in this spectrum. Okay, and those colours appear for a certain reason, which we'll discuss now. So if I look at a energy level diagram, let's say for hydrogen, and I could keep going, but I'm going to start here with n equal to 1. And keep going. So what happens is when an element receives an input of energy, its electrons jump from one energy level to another. What we notice is the electrons jump from one energy level up to another. Okay? Now, what happens when the energy levels jump? The electrons go to what's known as an excited state. So when the electrons receive the energy, they are excited, they gain energy, they go from the ground state, which is the lowest available energy level, up to an excited state. Okay? Now they can go up to a huge number of energy levels. But electrons only have a fixed energy, the quantum of energy. As the electrons are now in an excited state, what happens is they fall back down to other energy levels, and energy is then emitted as a photon of light. And this shows as a line in what's called an emission spectrum. And we're now going to look at the emission spectrum for hydrogen. This particular series that we see in the visible spectrum is known as the Balmer series, and it's as the electron falls back down to the n equal to 2 energy level from a more excited state, you get what is known as the Balmer series. So there's a relationship between the energy and the frequency of light absorbed. So this is the frequency of light. And this constant is known as Planck's constant. So each particular element, as its electrons go from different energy levels, each element will give off a very characteristic emission spectrum. So the hydrogen emission spectrum looks like this. So each wavelength of light corresponds to a certain energy drop, i.e. from one excited state electron back down to n equal to 2, and that gives off a photon of light which we see in its emission spectrum. So this actually is the same reason why fireworks give off a variety of colours. The metals within the fireworks themselves, their electrons get excited going to a higher energy level. As those electrons move back down to a different energy level, they give off a certain frequency of light, and so what we find is they give off certain colours, and each metal will give off a different colour. Okay, and that's the basis for flame tests for metals and also for fireworks. So just to clarify, when electrons drop to n equal to 1, we get the UV region of light. N equal to 2, we get the visible region. That's what we can see, that's the ones we talk about, that's the Balmer series. And as they drop to n equal to 3, they emit light in the IR region. Atomic emission spectra confirm the presence of energy levels within atoms.